Hello everybody. Welcome to the lecture on advanced recursive neural network. Today will be another one of those advanced lectures where we play around creatively with the building blocks we've learned about and look at a bunch of different applications. So I think it'll be a fun lecture. So a little bit of organizational stuff. PSET2, please carefully read the instructions for the submission. And PSET1, some folks submitted their PSETs in a way that was missing files and so on. So please carefully read the instructions for submission. Make sure you zip up everything that's in the folder. Please also follow Piazza for questions and some announcements. I think there are some small ambiguities in PSET2, the first TensorFlow problem set ever, I think. And so because of that, we'll also be a little more lenient on the grading, so don't worry too much if you just choose a slightly modified version. Again, TensorFlow is going to be a super useful skill for you moving forward. Actually, just recently, a new version of TensorFlow came out, so now it's actually faster than before. It's a really powerful tool for you to put together lots of different machine learning methods. So sorry if there were some ambiguities trying to put together the first TensorFlow-based problem set. You're very much at the bleeding edge now. If you have any requate questions or requests, please come to office hours or send a message to us and the TAs on Piazza. It's non-trivial to open that up in Gradescope, so we're probably not opening up in general for Gradescope, but if you have a real concern, just send us an email or ideally a message on Piazza or an office hour chat. And then it was a little tricky of a decision, but I think it's in the end best for your learning experience if we publish the solutions to the PSETs. So those will come online for you to be able to learn from them. Are there any questions on the organization? Yeah.
Will there be a collect submission scripts?
Probably. I think what we just announced on Piazza is to just zip up the whole file. Is that correct, David?
Yeah. Just zip it up and upload it to the docs folder.
So the entire folder of your PSET should just be zipped up.
And as for the solutions, will that include the code itself or just the written portion?
It should include the code too.
Okay.
All right, let's dive right in. So basically, we introduced these recursive neural networks last time, how we get the tree structure. In most of the lecture today, we'll actually assume we have a fixed tree structure, and we'll really focus on the kinds of features we can learn and the kinds of composition functions that take in as input two child vectors and then output a parent vector that captures the relevant information for your task. Now, there are lots of different combinations of these models. You can have different training objective functions like max margin functions that we looked at in last class. You can have softmax. You can even have autoencoder objective functions that try to just encode the inputs as well as possible so you can reconstruct them. We'll mostly focus in this lecture on the composition function. You can assume we often use a similar kind of softmax on top of each node. All right, so these are the different kinds of RNNs that we'll cover today. And we'll basically start with the simplest definition from last week, but then have different intuitions of phenomena that we want to capture and then extend the models more and more. And hopefully this gives you some idea also for projects and in general how to modify these neural network architecture. In fact, some of these we'll see here where we combine ideas from LSTMs and recurrent neural networks into recursive ones. And there's some papers now that combine some of these ideas also from recursive neural tensor networks, which we'll cover today, and try to plug them back into LSTMs. So you hopefully at the end of this lecture you get a little more sense of how you can creatively play around with the different Lego blocks that we've covered. And in the next lecture we'll actually try to review a little bit for the midterm. So if you have any questions from the problem sets, any issues, Please come with questions. If there are no questions, we'll probably not fill up the whole class on Thursday. But we'll just try to sort of reiterate over the content the most important aspects of the class so far. Are there any questions on the organization of today's and this week? All right, so today, in a week from today, we'll have our midterm, so you all have to be here. Those people watching the videos, you have to be here in class. Yeah.
Will the stuff in today's lecture be in the midterm?
Maybe.
Okay.
Less likely, but maybe. We won't ask you to go and derive all the nitty-gritty details, but you should have some understanding in general of the concepts covered in the class. All right, so one note that I want to make in the beginning is that while I will motivate each of these models with a specific task, such as paraphrase detection or relation classification or sentiment analysis, really all the models I'll introduce today can be applied to all the different tasks that we have. And in general, when you work with more and more complex models that have more parameters, you usually want to have harder tasks that actually require these more complex models and also larger data sets to actually train all the parameters that you have. Generally, it's tough if you have less than n training examples for m parameters and m is much larger than n, right? You want to ideally have more training examples than you have parameters in your model. Otherwise, it gets easier and easier for the model to try to just overfit to your training data set, and then it won't generalize very well. So let's start with paraphrase detection. It's quite a useful task. If you know whether two sentences have the same meaning or not, it could help you for summarization, for instance, getting rid of the same content multiple times. If you have 10 news articles, you want to condense it to one short news article, but capture all the important pieces that might be different and ignore whatever is similar. So quite a useful task for NLP. And here are just two examples that are rather binary. In many cases, and we'll get to that later today, the pure sort of binary paraphrase detection task has some issues, but it can be helpful for some systems. So let's read the sentences here. Pollack said the plaintiffs failed to show that Merrill and Blodgett directly caused their losses, versus basically the plaintiffs did not show that omissions in Merrill's research caused the claimed losses. So this is nice. There are some similarities, but generally these two have the same meaning. If one is true, then the other has to be true as well. So we often call this mutual entailment. One sentence entails the truth conditions of the other and vice versa. Whereas here is a very obvious example. The initial report was made to Modesto Police December 28th versus it stems from a Modesto Police report. One does not necessarily mean the other has to be true. Yeah?
I don't see why the first one mutually entails, because I can make the same argument of loss of information as the red text implies, because in the red text you're losing the December 28th, in the green text you're losing that it was Pollack who made the statement, right? And is that not relevant? Is that deemed like semantically redundant, or?
Okay, you're true, and in some ways you're right, that here you mention that Pollack said this, but if you assume that what he said is true, then this has to be true, and if this is true, then whatever, yeah, so it might not have been Pollack who said it, that it's true, and that exactly kind of shows you why I kind of prefaced this with it's hard to make this a fully binary task. Later in the class we'll actually look at semantic similarity, so we just say, there are, on a scale from 1 to 10 or 1 to 5, they're very, very similar and almost exactly paraphrases of each other, or not at all similar, and that kind of gradation is more sensible. But in most cases and in most data sets, people would assume that these two sentences are, by and large, paraphrase. But it's a good eye for detail. Yeah. So that leads us to the question: how should we compare the meaning of these two sentences? And the answer for us here is to actually try to compare the two by looking at the pairwise comparisons of all the words to all the other words in the other sentence, as well as all the non-terminal nodes of the tree to the other ones. So we'll look through this very carefully. What you see here is a visualization of the distance. So you can have, for instance, in our products, you can have squared, simple sort of L2 distances, and you look here at 1 through 5. So those are the 5 nodes of this tree versus the 7 nodes of the other tree. And then for each one here of these 5, you basically look the capitalized version of cats. How close is it to the word the? Not very, but then the second node here is very similar to the non-capitalized version of cats, and hence you have a small distance between those two word vectors. And so the first quadrant here is basically capturing all the similarities between the words themselves, and then in this quadrant we will capture the similarities between the non-terminal nodes and the word vectors, and then in the lower one here we capture the distances between all the phrases to all the other phrases in the sentence. Now, once we have this kind of similarity matrix, we have a lot of options. Now, we basically captured all the differences and distances between all the nodes in these two trees. And for now, we can just assume that this tree was trained with the recursive neural network that we had for parsing, for actually finding the tree structures. There are different ways you can compute these, but for now, we can just assume we have the tree structure given, and we use the standard RNN to compute the word vectors and the phrase vectors here. Now, what's the problem with this similarity matrix? Do you have any ideas for how to use this similarity matrix to classify whether these two sentences are paraphrases of each other or not?
Why can't you just look at the top, the root node similarities? Isn't that?
That's a great question. Why couldn't we just look at the root node similarity to classify these two sentences? That's actually a great idea, and that's exactly the idea that I also tried when I had this data set and I had the model, and I looked at the accuracy. And it turns out that it actually works somewhat, but it doesn't work as well. And the reason is that you do lose some information as you keep trying to squeeze more and more. Eventually this becomes a compression problem, right? You have here you have two n-dimensional vectors, and you squeeze them into one n-dimensional vector. And you keep doing that, and you inevitably lose information. And so while it works somewhat, and maybe if you had a very, very large neural net, a recursive neural net, then you may eventually capture some of that. But in general, it does not work as well. And so that's why we tried to capture all the pairwise distances. So let's say we have this similarity matrix. Why couldn't we just plug it into a classifier as is? Yeah.
Well, because, I mean, you might have two things that are very similar and everything else is not similar, but those two are important. The coordinates don't tell you the importance of the word in the sentence.
So the coordinates of the matrix, you say, don't capture how important it is that these two things are similar?
Yeah.
Okay, maybe, but it does help to know where they are in the tree. It does give you some information, right? So the fact that we have this structure means that there are certain words that actually align quite well with one another, given that they have this line. So this word and the following word and that following word have some correlate in the other sentence.
Because you can take that similarity matrix and maybe do further feature engineering, like look at the number in the similarity score of its adjacent matrices, of its adjacent entries in the matrix, and you can use that feature engineered to like a standard classifier. But that's basically what a neural network would do anyways. It would find those nonlinear combinations of adjacent similarities.
That's right. You could try to do a bunch of feature engineering on this, and in fact, I tried some of those. So I tried, let's just take a simple histogram of, how many are in how many bins. So how many nodes of this matrix are in the bin where there's perfect one-to-one correspondence. So mice minus mice is 0, distance, and so we have, one element in the 0 block of that histogram. Now the problem with that is the histogram would lose the positionality of where those similarities occur. So that wasn't ideal. But why couldn't we plug this similarity matrix into just a neural net as is?
Because different sentences will have different lengths.
That's exactly right, because different sentences have different lengths. So here we have, one sentence with 3 words, one with 4, and so we get this 5x7 matrix. But maybe I want to compare this first sentence with another sentence that has 20 words, right? So the change, this similarity matrix changes, and that's why I introduced this idea of a variable size pooling layer in 2011, which basically defines kind of like a convolutional neural network pooling layer, but instead of having a fixed size filter, it actually changes the filter, not the filter size, but the pooling area, depending on how large the input is and how many outputs you want in the end. So if you have, for instance, a 20 by 20 and you want to get 4 by 4 outputs or something, and you have a different size for the pooling regions than if you had a 30 by 30 matrix and you still want to get a 4 by 4 matrix out. Your pooling regions get larger as the sentences get longer. And so basically, we have this simple pooling layer that tries to find the smallest value. So this is not max pooling, but min pooling. And in each region, we find the smallest value in that region and then copy it over. And now we have a fixed size matrix, and we can just plug that into a standard classifier. And so we didn't have to engineer a particular feature around around this word. You have this many other words that are similar and things like that. Yeah.
Why do you use mean? Like, why don't you use average?
So it's a good question. Why do you use min pooling versus average pooling? Does anybody have an idea? So again, the elements of this matrix mean that when it's very small, there's an exact word that is in the other sentence as well. So it's a distance function between the elements of the sentence, the two sentences.
So you want to find the closest words and filter out, like for each subset that the middle matrix represents, you want to filter out the words that are further apart. You only want to look at the closest words.
Why do you only want to look at the closest words?
Because you want to eliminate noise, number one. Number two, because it probably helps your score function at the end.
Not quite. There's another very intuitive reason.
So, but isn't that a similarity matrix or is it a distance matrix?
So this one is a distance. It says, I mean, if we could, you're right. So the way I defined it when I talked about it is that this is going to be a distance. So the closer they are, the smaller it is. So it's technically not a similarity matrix. I mean, it captures how similar the sentences are through the distances.
So if you're like, if in those 4 things that you're pooling, there'll probably be like one phrase in this sentence that aligns with the other, and the other 3 will be like the other cross products of alignment. So you only want to take the one that's actually the true.
That captures it quite well. So basically, the fact that there's the somewhere here or there's catch somewhere here doesn't really matter that much to whether those sentences are similar, because you have basically a good correlate for these 2 words. So there are cats in both sentences. The fact there's the in the other sentence doesn't hurt the similarity as much. In fact, in almost all sentences, you will have lots of words that have nothing to do with the actual the first sentence. So intuitively, we just need to make sure that all the information in one sentence are captured in the other sentence at some point in some specific order. But it's okay that there are a lot of words here in this sentence that don't have any good match in the other. So like mice, catch, and the aren't in this one, but that doesn't hurt the fact that these 2 are similar. Does that answer your question? Cool. All right, so now there has been a bunch of work on that data set for a while, and in 2011, this paper outperformed a lot of other papers. In fact, this paper had won Best Paper at ACL, which is one of the top NLP conferences in the world. And this model has been very accurate. However, when I started looking at the errors more and more, and as we're getting closer to state of the art, I looked at some of the errors, and I actually felt like my model is kind of more correct than the labels of that data set. And once I saw that, I kind of stopped losing, or started losing faith a little bit in this Microsoft Research Paraphrase corpus, and started moving into other corpora that capture the similarity on a continuous scale. So it's interesting, and I think the model is interesting, and it's certainly useful to have a good sort of binary paraphrase classifier, but there's lots of nuance, and in the end it kind of depends on the humans and the annotators whether they really want to make that binary distinction. So there's a bunch of interesting visualization that fell out of this, and these are, again, this lecture is more about teaching you the methods rather than that exact method. It's not like I want you to create similarity matrices for whatever you do and so on, but I want you to try to think about when I come up with this kind of model and I put things together, where can I visualize? What can I visualize to understand my model better? Yeah.
How do these, does this modifier work on two sentences that say very similar things but present the opposite? The report was whatever, the cats eat mice and cats do not eat mice.
Mm-hmm.
Very similar sentences and might have high weight size similarity, but it's not this very important.
And you can only hope that the knot is somewhere captured in these in this matrix somewhere through the. Basically, as you backprop, if you had a large enough data set, which again was a problem with this one, we actually had to come up with an unsupervised method to learn these. But if you had a supervised training method, then, and you had knot somewhere at the top of this tree here, and you backpropagate through everything, then it could learn that knot should change the similarities at the top node of the tree significantly. And so that is, in theory, possible for the model to learn as long as it sees negation in those kinds of examples. Fortunately, those were not, there are no such examples. The way this data set was created, which is also a little problematic, is they took a simple machine learning model, put it together, and then essentially had a large news corpus and found very similar sentences, and then took those top sentences and then distilled them from one another, say, into these two classes. And so they only captured sentences that often had at least some overlap, and there were no news articles that say this didn't happen, right? So this is also a great question that points you to trying to be very careful about how you collect your data, how you label it, and what kinds of assumptions you're making about your domain and the way you collect your data. So if you, for instance, there are a lot of horrible papers on analyzing Twitter data that just say, oh, people in this area are more racist, or they use these kinds of words. And really, in most of these beautiful heat maps that you see, you basically just see, well, if there are more people living in this area, more people will use certain kinds of words, right? So you have a lot of frequency statistics that are captured in a lot of these papers. So you want to be very careful about your data set, and I don't think this data set is like the best data set in the end for capturing similarity. Yeah?
And how do you choose the size of your pooling layer?
That's a great question. So that was just chosen. You have train, def, test set, and you basically just cross-validate over the size of the final output layer here. So this one is I think a cool visualization because it does show us some of the interesting things that the model can do. So here you have two very similar sentences, and you actually see in your similarity matrix that there's really great alignment between the two. So you see here that there are certain blocks that are perfectly overlapping, and once you have these blue ones, which means very small distance between even non-terminal phrases, you know that they're actually perfect string matches. So in some ways, this captured string matches. And so here you have the ground truth label is indeed that this is a paraphrase. The probability that the model returns for this being a paraphrase is very high, and it is 1. This one is interesting because it kind of shows us, 1, the model can deal a little bit with ungrammatical sentences, and 2, it can deal with sort of flips of entire longer phrases. So here the lies and deceptions from Saddam have been well documented over 12 years versus it has been well documented over 12 years, of lies and deception from Saddam. So a little ungrammatical, but probably trying to say the same thing. And the way this is captured in the similarity matrix is basically with these two off-diagonal lines. Here we can see, all right, the model is better than just capturing straight up lines like this. And actually, even when there's not perfect lines, it works reasonably well. This is the example that we had before, but it's not as obvious of a paraphrase either as some of the other ones. Now this one is interesting in that the model just barely got it correct that this isn't a paraphrase, and despite having a very nice overlap here between the different phrases. Now this one is fascinating too. So here you have this gap in what looks otherwise like an almost perfect alignment between all the words and the whole content and all the phrases in the sentence. So where does this gap come from? Let's pick somebody else. Yeah.
I'm missing years and the part of the content.
You're missing what?
The dates. Your second one.
You're missing the dates, that's correct. And you're missing really that entire phrase, which is that Henry Kissinger was an ambassador at large for counterterrorism from 86 to 89. So basically that breaks the mutual entailment relationship. Now one sentence can be true and the other one doesn't necessarily have to be true with a lot of different facts. And so these aren't paraphrases. And then this one, if you can still see it, is fairly obvious, very little overlap between any of the content. All right, so that was one particular example of a model for paraphrase detection. Are there any questions around this? I left out a couple of details here on this model, but yeah.
So if you had the second sentence subsume the first one somehow. So I said I will do this and I didn't do it versus I deceived you. You don't have much word similarity, but one is a paraphrase of the other.
So you don't need to have exact word like string matches, right? You can just have similarities. So what are your examples?
So let's say that the second one is something higher level, like I deceived you.
Okay.
And the first one is some expanded version of how I deceived you.
Oh, I see. Okay, so just to repeat it for the videos, basically the idea is one describes some complex interaction, like I walked over and I pretended like, you know, this thing was going on, but it really wasn't, and the other one just says, I deceived you. So one, they're not paraphrases, so because you can have a lot of details, and that, you know, it's a singular direction entailment. And so entailment by itself is actually a much more complex problem in terms of at least most of the data sets than just pure similarity. And we may actually get to entailment in later classes. There's a really great data set that just came out by Stanford a couple of months ago that is really the first data set that's large enough to deal with entailment in a principled way with neural nets. But you're right, that wouldn't necessarily work in this model. Yeah.
So let's say I trained this model. If I wanted to feed in two sentences and had to tell me if they were a paraphrase or not, there would have to be some pre-processing, I believe, to get the parsing right?
That's right. You'd have to first get the parse tree structure, and then you could apply it to this trained model.
Okay, okay.
Yeah. Yeah.
So this is not related to this model, but paraphrase detection in general. It sounds like paraphrase detection is a lot like trying to figure out if, like linking it to machine translation, is like trying to figure out if these two sentences would translate to the same thing. So I'm wondering if you used a method like the machine translation model from a previous lecture and said, okay, this state at the end of my source language sentence, and then you compare that hidden state for two phrases, would that work well for this task? So
the question is, could you use machine translation models to for paraphrase detection? And I think the answer is absolutely. I think nobody has really done that in a principled way and shown like, here's a really great state-of-the-art neural machine translation model. Let's apply it. There have been interesting sort of visualizations and intuitions, but nobody has done a proper, careful comparison of this, and I think it would have a very good chance of working quite well. Cool. All right. So now let's move on to a slightly more advanced model and some linguistic intuition of why we might want to use this. So we started out with the simple R and N definition where we just take child on the left side, child vector on the right side, concatenate them, single layer neural net to compute the parent. And then basically we realized, well, that was kind of tough. There was only one W matrix, one single layer that now has to capture all the complexity of combining different types of words. And that is asking a lot, right? It's asking a lot of a single layer neural network that just has these two linear combinations and a squashing function to approximate all the different complexities of language. And so we had introduced in last lecture to have sort of linguistic intuitions of which word types have, and then word types had different W matrices. But maybe what we would like instead is to have the model figure out what kinds of transformations to use itself without us telling it exactly this particular category, like an adjective or a noun. And still capture that we have sometimes words that act more as operators. They don't have that much meaning in and of themselves, but they really change the meaning or amplify it of another word. So for instance, if we have very good, then very is really can be seen as an operator on the word good, amplifying the goodness. And so I proposed in 2012 a different kind of composition function, and this now, I was trying to really show you the things almost looking like Lego pieces. But basically the intuition is, let's have every word not just be represented by a single vector, but by a vector and a matrix. And whenever you combine that word with another word, you actually apply the matrix of one to the vector of the other and vice versa. So let's untangle that a little bit. So let's say A here is the word vector for very, and capital A is the matrix for the word very. And it's just simple, everything is two-dimensional, just for illustration. Again, mostly those vectors and matrices will be higher dimensional. Then we have B and capital B, and we have movie here. And now when we combine very good as a phrase to compute the parent here, what we would do is we would take the vector of B, and that vector will be multiplied by the matrix of A, and the matrix of B will multiply with the vector of very. Yeah?
Sorry, I'm confused. What's the difference between the vector and the matrix of any one of those?
What is the difference between a vector and a matrix? They just capture different things. So for instance, intuitively, very might not have much of a meaning, but it should have a very different operator. It should make something that's followed by it, like an adjective, amplified and stronger in its meaning. Or maybe it should rotate it and go push it in the other direction if it's not, right? And so not now might have a much more powerful way to really change the direction of whatever it's being combined with.
So how is that different than just a weight matrix then? I mean, is the vector the input of the...
So these are all weights. We will learn the vectors and the matrices for all of these words. They're all just different parameters of the model, and we let the model figure out how to change these parameters to achieve a lower cost. Yeah?
How do you initialize the matrix?
It's a great question. How do you initialize the matrices? So there are actually a bunch of interesting thoughts around this. One is, what if you have 100 by 100, like 100-dimensional word vectors? You got these great word vectors and you really want to use them. 100 dimensions are great. But now you have 100 times 100 times the size of your vocabulary for all the matrices. And so what you actually end up doing instead is often to have a low-rank matrix. Can you raise your hand if you're familiar with low-rank matrices? All right. Probably enough to not go into details. But basically, you have, let's say this is an n by n matrix. You can have two matrices that represent each one. One is n by r, and the other one is r by n. R is much smaller than n. And so when you multiply the two, you get an n by n matrix, but you really have fewer parameters, and you kind of assume everything operates in a lower dimensional space. And you often add, additionally to that, another vector on the diagonal. So maybe I'll just write it down really quickly. To have fewer parameters, you often describe this as some diagonal matrix plus uv. So this here's a z matrix, a z vector, this plus this n by r times r by n matrix, where this is u and this is v. And so those are going to be really the actual matrices for all the word vectors. Yeah.
So because your matrix is low rank and because you're conceivably learning random operators, isn't this kind of like random projections, basically?
It starts out, certainly these operators start out as random projections of a word vector to another word vector. So these intermediate ones here.
Reduction, where you do random projections to learn like the manifold that underlies.
But so the matrices here are learned, so they're not random. Right? So we do backpropagate. Imagine having on each of these nodes here, again, some objective function that you add and you propagate through, and you have an objective function at every word and at every non-terminal node of the tree, and you apply the chain rule, you run backpropagation through structure, and you change all these parameters. So you're going to take derivatives with respect to all these different ones. So this is kind of the general definition of the matrix vector, or MV, R, and N. Yeah.
So you like adjusting the learning rate for the operating matrices differently. How do you kind of balance interplay between the overall weight matrix W and the operating matrices?
So the question is, do we adjust the learning rate? We don't. Well, we actually let AdaGrad just figure out which learning rates it thinks would be relevant. And if it thinks there's a commonality between all of these, it would focus more on W, and if not, the model would focus more on these specific ones. Cool. So now we can look at this very simple data set just to see if this idea actually works. And again, I think there's some good ways here for you to visualize and think about visualization. It's less about the exact model. But what we had here was a pretty cool data set actually from Chris Potts, who collected a lot of different bigram statistics of how often do you see a certain bigram in a very, very large corpus of movie reviews, and then and how often you see each bigram for 1-star movie reviews, 2-star movie reviews, up to 10-star movie reviews. So you would assume, for instance, and this one is mostly predictions. This one is one of the few that actually shows the ground truth. This was one of the training examples, or one of the ways we can really test the accuracy. And so, for instance, not sad, we would see a very mild sort of U-shaped curve here, but mostly it's almost kind of uniform. So you saw out of the total number of movie reviews, how often you saw sad, and 20% or so of the times you saw this bigram not sad, it was in 2-star movie reviews. So, yeah.
Sorry, what's the y-axis and x-axis again?
So the x-axis these are essentially bins. We could really write them more as a histogram, but it's normalized to sum to 1. So if you have 10,000 times you saw the phrase not sad, then 22% of those you saw in 2-star movie reviews. And rarely ever did you see the bigram not sad in 6-star movie reviews. So it's kind of a normalized histogram. So you kind of get a multinomial distribution out. And now you can train your softmax to try to predict that multinomial distribution. And that's actually a really great exercise for you to do too. We looked at the softmax and the cross-entropy error training usually in terms of having a one-hot vector, where we have one class that is the true class. But really, you can assume you want to predict that it should be 0.5% probability, or sorry, 0.5 probability on class 1, and 0.5 on class 2, and 0 on class 3, 4, and 6, or 3, 4, and 5. Right? So you can actually predict a distribution instead of trying to always predict this one-hot distribution. And all the math for minimizing the cross-entropy error actually works out, and in the end you can try to just visualize the distributions that you predict instead of just taking the max for the single class. So that's what we've done here. It's the same softmax cross-entropy error combination, but we actually look at the outputs of all the different probabilities and we train it to predict the entire probability distribution instead of just a one-hot distribution. All right, so now let's look at basically here the outputs of what this model thinks and how often it would think to see certain bigrams. So in each row, we have the same adverb. So fairly here is our adverb modifying the adjective at each column. So fairly annoying. Fairly, we often call in linguistics an attenuator. It attenuates, how serious that adjective is in whatever direction. So annoying by itself would be quite negative, but fairly annoying, not as negative, still with a slight bend towards the negative. And here we basically look at a comparison of training a standard RNN versus a matrix vector RNN to try to predict these distributions. Yeah?
I had a quick question just about the MVRNN structure. So only the word vectors get these vectors and the matrices, but like intermediate states, they just have the...
Oh, great question. So what about the intermediate states? Really good question, because I kind of glanced over this and it's not even obvious from this, this visualization. You will actually also have a vector. You can have lots of different models. The simplest one is to just multiply the two matrices, for instance, and then you get a parent matrix out for the parent vector too. So there will actually be a separate neural network structure that takes the inputs as matrices and outputs another matrix. Yeah, great question. So every node, both non-terminal and terminal, have matrices associated with them in this model. All right, so fairly awesome, attenuates awesome a little bit, but still quite positive, and fairly sad, relatively flat. Now where it gets interesting and where the RNN kind of broke down, and that gave us a lot of intuitions of why straight up recursive neural networks might not be powerful enough to do eventually exactly the question that you raised, which is for paraphrase detection, should it really be able to change entirely what the direction is? And here we saw that not annoying, for instance, the RNN cannot really change how overall annoying this is, but saying not annoying, you assume it flattens out somewhat and is not as negative and mostly seen in negative reviews. Likely not awesome, the RNN still makes it very positive when the MVRNN is able to flatten it out a little bit and attenuating and changing awesome. This is also a good example of why logic is not a perfect description of language, especially when it comes to sentiment, right? Because saying something is not good kind of makes it bad, but not awesome, actually it doesn't mean it's terrible, right? It's just not like the most awesome movie you've seen, but it could still be a fairly decent movie. And so negation isn't perfectly logical in sentiment, and this kind of distribution visualization shows that. And this one is kind of fun. So unbelievably annoying, very negative, unbelievably awesome. So unbelievably is an amplifier, ticely strengthens whatever the adjective here tries to convey. And then this one is an interesting shape. It's called the U shape for obvious visual reasons. And interestingly, unbelievably sad, the model thinks would appear often in very negative reviews as well as in very positive reviews. Why do you think that is?
The context, right? Unbelievably sad, as in I went to see a really sad movie and it was really sad, it was awesome. And unbelievably sad, this movie was really sad. Like, it isn't really bad.
That's right, it isn't really bad. Like, unbelievably sad performance of the actors or something versus just a tearjerker movie that people like to see, like Titanic or something. And so linguists analyzed these different curves and gave them different names, and this is like the U-shaped curve, and it's cool that the model kind of predicts this for unseen bigrams by itself also. And so sometimes students ask, like, could this project give a good grade or not? And it's very hard to say, because if you come up with some interesting visualization like this of the same model, and one report just says our final accuracy was 0.5 or something, And the other report says our final accuracy was 0.6 because we tuned it and it worked a little bit better. And here are all the visualizations, and here's what we've learned about the model and the kind of interesting linguistic regularities that the model picked up, and so on, and some examples. It just changes the grade a lot, and yet it's the same model and maybe even the same accuracy overall, but one is very carefully analyzed. And so I want to encourage you to start trying to visualize your models and the outputs of your models very carefully like that. All right, so now the MVRNN, we tried it for something else, which is a very different task, and basically one where we tried to classify relationships between words. So if you want to build, for instance, a very large knowledge graph, want to find all the capital cities or more complex cause and effect kinds of things. So this drug caused this, side effect or something like that. You might want to be able to go through it, label a couple of examples, and then apply that model and extract from all of PubMed or a very large corpus all potential side effects or things like that. And so this one is a fun data set from a semival competition. And basically, it's a nice data set, but it's actually quite small in the grand scheme of things, especially for neural networks when you try to train everything. But here are some of the examples and what the predicted relationships were by this model. So here, avian influenza is an infectious disease caused by type A strains of the influenza virus. And so what this model the goal of this would be to say, all right, there's a cause and effect relationship here between influenza being the effect and the virus being the cause of that effect. And the way we will do this is by basically taking the words and marking them up, and then taking the subtree that is the highest node that basically dominates these two child nodes transitively, or terminal nodes of the tree. And then basically on top of that node in the tree, we just have our standard softmax classifier again. We train standard cross-entropy errors, and then we can mark any two words at test time, look at the parse tree, where do they actually connect in the parse tree, and then put the classifier on top of that. And again, we assume we have the Stanford parser that has given us the tree to do that. And so when we look at the results, so this was a competition, and if you've ever run or partook in a machine learning competition, you'll see that towards the end, people just try to add as many features as they can to squeeze out more performance, and that's kind of what we've seen here. So the top model used part-of-speech tags, WordNet features, so large human-generated taxonomy, decades of work, prefixes and other morphological features, so when it starts with different kinds of prefixes, especially for the biomedical domain. You might have tetra or something that makes it more clearly like a type of drug or something. Because twice. Dependency parse features, so run a different type of parser that tries to extract relationships. 11 classes, PropBank, FrameNet, so lots of other human-engineered types of information. FrameNet actually gives you, in some cases, and TextRunner too, some of these relationships already, so they're completely separate, very large machine learning models. In the case of TextRunner, that goes through like millions of examples on the internet to try to extract relationships. One of them, I think, was cause and effect or instrument and agent, and that actually falls out of TextRunner, so it's a little bit cheating. But then Google Ngrams, gigantic corpus of billions of Ngrams. Another paraphrase system, again, yet trained machine learning system put together, and so on. And they got 82. And then we tried to train this with just these different recursive neural network architectures. It's the standard RNN and the MVRNN. And the MVRNN got better, but it was just not able to compete with this, largely because the training data set was just not large enough. And you couldn't generalize certain examples from this small training set. So we ended up, somewhat begrudgingly, also adding 3 of the features in order to say and be able to publish the paper and say this is the state-of-the-art model now on this task of relation classification. Nowadays, I think the better thing to do would probably be to just collect more training data, and then you wouldn't have to use any external features. All right, now on to sentiment. We've covered it a couple of times, and I wanted to dive a little bit more deeply into it because it's a really fun task. It's super useful. It's one of the few NLP classifiers that is actually useful across the board, in the sense that most classifiers for most companies out there and most individuals are very specific to that company or individual. You want to answer emails and classify, who should answer this email or something like that. Then depends on your organization and what kinds of emails you get. So it's your special classifier. But sentiment is one of those things that's kind of useful across the board. Financial services companies want to find, or financial trading companies want to find like what's positively being said about this stock. Movie review people want to find like what do people love about this movie to understand, what kinds of things they want to incorporate in the next action movie and the next sequel or something like that. So lots of different applications for sentiment. And there are actually some fun ones. This one is a good example from 2011 where the mentions of the name Anne Hathaway, the actress, seem to have a huge effect on the stocks of the company Berkshire Hathaway. It's a great example of missing entity disambiguation and of applying sentiment really in the wrong way, but it does show us that clearly there are already some algorithmic trading companies that are trying to do this, and I'm sure since 2011 they've improved and learned from those mistakes. So when you go out into the real world, you'll see a lot of people, and this is still true today despite clear evidence that it's not ideal, that start with bag of words models and then add linguistic features, lots of processing and sentiment lexica that say, all right, these are all my positive words, these are all my negative words, and I know my domain, I know like hip hop or real estate or whatever my domain is, and I collect all these words. And of course, those kinds of methods, you will get somewhere, but they will never transfer as well either, because you might say surprising, for instance, it's a positive word if you have movie reviews or book reviews, but then you talk about cars and the steering is surprising, it's not as ideal, right? And so it's, again, this discrepancy between trying to learn your features from just training examples versus trying to design and tell the model what you think the world is really like. And then another major issue, of course, with all these bag of words models is that they do not generalize very well and don't, in some cases, just are unable to distinguish very important differences that fall out of the word order. So if you have, for instance, white blood cells destroying an infection in some biology text versus an infection destroying white blood cells. Well, if one is written in your medical report, you might live, the other one you might die. So sentiment is fairly clear. But if you just use the bag of words model, it couldn't capture the difference because they have exactly the same words. So most people think, okay, it's one of the easier tasks, and certainly compared to machine translation, for instance, where you have to capture and generate all the possible sentences of the English language, it is a simpler task. But it's only for longer documents where the word order stops to matter do you get sort of low 90s in accuracy. And that's often the case. The longer the document, the less the nuances matter, the less it matters that you negated this here and there, because you use enough words over a longer document to kind of tell you what's going on. So you can, if you have a word awesome, unless it's quoted from the text of the movie or something, as soon as some review mentions the word awesome, you can say a lot of things around it. It's probably a positive review. However, for a data set of single sentence movie reviews from Pang and Lee, who kind of started sentiment analysis as a task in NLP, the accuracy had never reached over 80%. So when you look at a single sentence and try to say is this positive or negative, nobody got above 80. And that's kind of sad because it is it's not that high. You should be able to get more accurate than 80%. And when you looked at the errors that the models were making, it was clear that they weren't able to capture negation and its scope and other semantic effects. So let's look at some examples here. So this one is stealing Harvard doesn't care about cleverness, wit, or any other kind of intelligent humor. Right, pretty scathing review, very negative. But to most of these bag of words models, it has humor, it's intelligent, it's kind, wit, cleverness, care. So there are kind of 6 positive words in this sentence. And so most normal sentiment analysis models would say this is all positive. And then there's one little doesn't in front of it that actually makes it all negative. And in here, there are slow and repetitive parts, but it has just enough spice to keep it interesting. And so here we have a so-called contrastive conjunction. So this conjoins 2 parts of the sentence, but it contrasts them. And so usually when you have any kind of structure of some phrase X, but some phrase Y, pragmatically, you're contrasting the positive with the negative, and the latter part of the sentence matters more for the overall sentiment. So despite having slow and repetitive parts here, you're saying this is still interesting. And so this should be a positive sentence. So we looked at the state of the art in sentiment analysis. We looked at the data sets that were out there for us, and we looked at the models that were trying to combine words. And we know from a previous model on the MVRNN that the negation is hard to capture in the standard RNN. And we looked at the data sets, and we also realized, well, none of the data sets really tell us, 1, they're not large enough, and 2, they're not telling us when something is negated. And so what we did is actually create the Stanford Sentiment Tree Bank, where we parsed the original Pang and Lee data set of 10,000 sentences, and then we asked human annotators to label every single subphrase of those 10,000 sentences, or roughly 11,000 sentences. So really in total that costs like maybe $8,000 or so, and one master's student a couple of weeks. Nowadays I think you can, if you know how to do it, as in you have a little slider, you have a standard thing, you can get that with less money in 2 or 3 days. So this is also one of the big practical changes in the world. Like 20 years ago, you just couldn't ask 10,000 people to just rate 100,000 phrases really quickly for you. Nowadays you can. And it's not that expensive to collect label training data through crowdsourcing tools like Amazon Mechanical Turk. So we had here the original 11,855 sentences. They were split into 215,000 unique phrases. So there's a lot of overlap between them. And then each of those phrases we took in isolation, so not showing the rest of the sentence, and just asked nerdy folks, is this positive or negative, or phenomenal, fantasy, bestseller? Is this, on the scale here? And we actually asked each phrase to be labeled 3 times, because one person might make a mistake or it might be subjective. And of course there are certain things that are just inherently subjective, like you might say, this is a great movie for frat boys. Well, your New York intellectual is going to think that's a very negative review, but your frat boy will think it's a great review and would love the film, right? And so it depends. And there are certain things that this doesn't capture either, right? Because we're going to only look at the mean label, but some might be very bimodal, like the example I just gave. So this is a really cool visualization from Jason Chuang, one of the co-authors and HCI PhD students back in the day here at Stanford. And I love this visualization of the data set a lot. There's a lot going on, but it puts so much great sort of content about this data set into one figure. So let's disentangle this a little bit. So on the x-axis here we have n-gram length, and here we have the percentage of sentiment values. So if we start at n-gram 1 as in single words, what this basically tells us is the relative percentages of words that have been labeled very negative, negative, somewhat negative, neutral, somewhat positive, very positive, and extremely positive. So basically these 5, these 7 different labels here. And what we see, one is people often, the larger elements for each n-gram here means that the position were actually exactly on the ticks of this slider. So people didn't realize, or in some cases just ignored, that they could leave the slider like in between 2 ticks and actually put them exactly over them. So that's an interesting observation. Most interestingly, we see that when you look at words separately by themselves, the majority of them are neutral. And it's really, I mean, this is a specific data set that was collected for movie reviews, so, and originally from Rotten Tomatoes, so we'd assume we'd get more sentiment. But interestingly also, there are always sentences that were considered neutral no matter how long the phrases and sentences were. The original data set was only positive, negative. So we already found a problem with this data set that hundreds of researchers have worked on, and we haven't even started doing anything cool on the deep learning and modeling side, right? There's already an issue that it wasn't just a binary positive, negative, and this kind of issue is similar to the one for paraphrase detection. And then we also saw that when we kind of cluster, very few people ever used the most extreme labels of very positive and very negative. It kind of makes sense to just cluster and combine the negative and very negative labels together. All right, are there any other interesting things we can see from this plot?
What do the lines mean again?
So the lines are just kind of basically groups of how often certain values were used in between the ticks.
Oh, I see. So there were distinct ticks within the ticks.
That's right.
Okay.
Just kind of, you can see them as bins and frequency like thresholds. All right, so now when we applied a bunch of these different models of training with just the original sentence labels, but fixed, assuming we say, all right, let's ignore all the neutral sentences and just delete them from the data set to make it easier and somewhat comparable, but not completely flawed. We took simple models like bigram naive Bayes, recursive neural networks, and matrix vector recursive neural networks, and we just trained with the original way, cleaned up, where you just have a single label for the overall sentence, versus you actually have labels for every single subphrase of the sentences. And in the case here of the simpler models like bigram naive Bayes, the idea is just each of the phrases is a completely own document, its own labeled instance. Now what we see is, well, more data always better. That's the sad truth. In many cases, when you start with a machine learning project, you say, I just need to get 3% higher accuracy, and then my client's happy or whatever, I get a good grade. The simplest thing in almost all cases is to just collect more training data. And only once you've done that, you'll see, all right, now we collected more training data and we moved from 80 to actually like 83. So that's pretty significant, given that the state of the art of all these different kinds of models had always been just around 80. But we also see that, somewhat sadly here, our fancy recursive neural networks are actually getting slightly outperformed by a super simple baseline. So that means that while we captured more facts, clearly this can't capture all this complexity that we're talking about with negation. So the hard negation cases were still mostly incorrect. And that now is a great motivation to actually find a better model, a more complex neural network type architecture that should be able to get this right, especially for things like negation. And that led us to the recursive neural tensor network, which is the last sort of model of my PhD, which is much more expressive than all these previous architectures, and it allows more complex interaction between the different words and phrase vectors that we're combining. And so now again, we have these basic Lego pieces. We're going to put them together in a new way. We won't go through all the details, but I give you kind of a summary of the math and how it's different at the end. So let's see how we might want to do this in order to allow basically one word to have not just additive interactions, which we've mostly captured so far, but also multiplicative interactions. Because very, very simple, on a very simple intuitive level, if they have multiplicative interactions, then if this is negative, you multiply the two, well then maybe they can become positive, right? And so this is what we did. Let's say we have the simple phrase, not very good. Very is now again just a simple vector B. Good is the simple vector C. And what we're going to do is we concatenate the two, just like before. But now we will have this bilinear product that is modified by the matrix, or sort of guide it in how you want to have the inner product of these two concatenated vectors changed by this matrix V. So what's the dimensionality? Let's see, these are all column vectors. This is, and you know, every word vector or phrase vector is two-dimensional. Hence we have here this 4x4 matrix. What's the final dimensionality of this product? 1 by 1, that's right. So we have here a 1x4 times 4x4 times 4x1 matrix. Look at the outer numbers and you get this is just a single number. So now that single number might tell us something, but we want to have the output be recursively compatible, so we can take the vector that we might get P1 and again apply this to the next word and next composition. And so what we did is we said, well, let's have a different set of another matrix that now allows us to governs another way these two concatenated vectors could interact, and just concatenate the final outputs of these two bilinear products. And in general, if we have n-dimensional vectors, we'll have many of these n by n matrices. Sorry, of these 2n by 2n matrices. So each matrix here is 2n by 2n, multiplying these two n-dimensional vectors. And if we want to get, in the end, n outputs, we need n of those. Do you have any questions?
It seems like a lot of parameters.
It seems like a lot of parameters, but let's think about this. So let's say you have 50 dimensions, right? So you have 50 times 100 times 100. But when we had the matrix vector Rn, you had for each of them in the, let's not assuming we have this lower rank, you have 100 by 100 for each of the words, and now you have 100,000 words. Right? So it's 50 times 50 times 100,000 versus 50 times 100 times 100. So the RNTN actually has a lot fewer parameters than the MVRNet. But it does have, more than the standard RNet.
Do you do any low rank factorization here as well?
We don't need to do low rank. It's actually, in the grand scheme of things, these are not that many parameters, so there's no need for low rank here.
Is it straightforward to implement this in TensorFlow?
So this is many years prior to TensorFlow having come out. I had to do all those derivatives and derivations by hand, including for the matrix vector Rn, which is annoying. I think, given that this is essentially a tensor, I would assume it's pretty easy to do in TensorFlow. It's just essentially an three-dimensional tensor. Yeah.
Do you now use your tree searches, or do you use pre-constructed trees?
That's a good question. So for all of these models, I have assumed and continue to assume we have the tree structure fixed and given by the Stanford parser. All right, so now we have one vector. Now, for good measure, we'll just throw in the standard Rn. Now, this is basically a more general model. If all the v's were 0, we fall back to the Rn. And this is essentially one slice or one computation to compute the parent vector at one node. And now this p vector here will again have the same dimensionality as each of its children. And so we can recursively combine that and have the same exact computation at every node. But now it's a much more powerful interaction between the two vectors. And now, if you want to derive the main new matrix derivative that you need to see for each of these slices is the derivative with respect to x here. If you have something like A transpose x times A with the derivative of that with respect to x, which is really just A times A transpose. So, and again, if some of these are not super intuitive and it's been a while for you to do that, or you've never done it, you can just, again, write it all out as one gigantic sum, right? This thing is just a single 1 by 1 number in the end. And you take the derivative with respect to x11, first element of x, and you just look at what that comes out as. You do it with x12, x13, and you look at like xij, and then you see, oh, well, I in the end need the cross product of all these different ones, and it will fall out. Similar to the gory details that we've done in the beginning. And now, don't be shocked, but this is the final math that comes out. Back in the day when you had to do this manually, of course now you just throw it into TensorFlow and you just don't even have to do this. But it's still kind of interesting to look at it. So, and in theory, none of this should be super surprising given this one new fact. So we start by having our standard cross-entropy error with some regularization on all our parameters. And here we have our target distribution for all the nodes and for all the classes at each node. We have our standard softmax error message that's coming in. And then for each of the slices, we basically have part of the delta error signal that comes into that slice and the outer product here for basically this parent, the two children vectors concatenated. So that's just the output. And then the main backprop rule changes here in this way, where we have the standard W transpose times delta times Hadamard product of F prime of our lower layer, plus this S term. So the S term here is the main novelty from this model, and that comes out to be essentially this summation here of each slice plus its transpose times again the child vector. So this part is the new piece that as you go through all this math and you do this, comes out. And then again at the end you'll have the delta that comes in at the softmax at this node plus that one from your parents, and you propagate that down the tree. In theory you should be able to do this, but I don't think you have to worry because there's no way we can ask this in the midterm, just because it's not hard, but it just takes so much time to go through it, and it's so easy to mess up little indices and stuff that you don't have to worry too much. Yeah.
What nonlinearity did you use on the output of the vector?
10H. Back then, rectified linear units weren't invented yet, and I just used 10H.
And that didn't result in a problem because of the square term giving you extreme values and zero gradient?
Nope. You initialize them all in pretty small values, and it was pretty stable actually compared. So one obvious comparison you might ask is, well, why didn't you just have a deep network at each layer? You know, like a 5-layer neural net at each node of the tree instead of having one such layer. And those actually blew up like crazy and had like exploding gradient problems all over the place. Cool, so now the new model actually pushes another 2% or so. And now we've reduced the overall error from roughly 20% down to 15. But what's interesting is the examples that we now get right. And so again, this is what I would encourage you to all do very carefully in all your analyses of your projects. So the first analysis was, well, we know now not just binary, positive, negative, like this. This was basically done so we can compare to the past state of the art on roughly that data set in numbers that are, you know, understandable to all the previous researchers. But what we're trying to push for is to say, well, the world is more complex than just positive, negative. Really what we should look at is fine-grained. And you can look at fine-grained not just at the root, but at every single node of all those trees for all the syntactically plausible phrases. And basically here, the RNTN, the recursive neural tensor network, did very well and had, you know, for the first time pushed some of these models to be above 80% on all the different roots, and this is very negative, negative, neutral, positive, and very positive. So it is better able to get the different gradations. What we also see that's interesting is that while the simpler models, naive Bayes and bigram naive Bayes, really do very poorly in shorter phrases, the longer you get, the less pronounced the differences are. And that's again very intuitive in the sense that the longer the sentence is, the more it's like a document, the less, you know, some negation matters because you're having so many positive things for average things. But if you really have like not very good or not very awesome and things like that, it's really important to get the compositionality right. And the RNTN kind of almost upper bounds most of the other models at most of the different n-gram lengths. Now this is where it gets really interesting and where, what I would like to encourage you to also try to do to analyze your models carefully. What we did here is basically we took some positive sentences and we, without knowing what the output of the model would be yet, tried to change some sentences with the smallest amount of change possible to actually change the entire sentiment. So it started out with the sentence, Roger Dodger is one of the least compelling variations on this theme. And now we said, well, how could we make that sentence from being so negative to being very positive? Well, just one word needed to be different. Instead of least compelling, we'll just change least to most. Most by itself, still a neutral word, but now this actually becomes a very positive sentence. And the RNTN was very accurate at this special data set that was kind of extra hard, right? Because in general, people use certain words, and most models are quite easy to fool if you just change that one word, because it kind of captures the overall statistics of everything. And so when we looked at this negation subset of the data, that's when the RNTN really shined. And we looked at having all the positive sentences and how much of the probability mass was taken away right at the nodes where negation was added. And so we saw here that RNTN was able to really take out a lot more probability mass from the positive classes and put it towards the negative classes in these negated positive sentences. Yeah.
How did you compute the per node probability mass?
You just look at the output of your softmax, which is a multinomial distribution, and then you can look at how much does the change from having probability mass on very positive and positive versus on negative and very negative afterwards.
Wouldn't the softmax give you the per phrase probability? And
that's right. So you can have all the non-terminal nodes and all the phrases. All right, now, then we were thinking, well, okay, maybe all the RNTN was able to do was to say, whenever I see something that's a negation, let's just make things more negative. And that, again, wouldn't have been as interesting. So we looked at what happens when you negate negatives. So really, we don't want to necessarily have flips, but you should have more positive activation in your multinomial. So here's an example from the model. So not and bad. So not actually often appears in negative contexts, which is an interesting side note for you psychologically. If you use a lot of negation, there's a lot of negativity that just comes from using negation words. Bad, very negative. But not bad actually turns out to be mostly neutral and somewhat positive. And I guess if you're collected the data set in Great Britain, or like British, maybe it would be even more positive. But for American English, it's basically not bad. It's mostly neutral, slight hint of positivity. And here's a real example. It's just incredibly dull versus it's definitely not dull. Not dull, again, doesn't necessarily mean it was the most exciting movie, but it's not dull. And so the cool thing was that here the differences were even more pronounced when we negated these negative sentences with very small changes. The RNTN has now an even bigger gap over the simpler baselines. And most interestingly, it was actually the only model that captured this effect at all of the models we tried at the time. So none of the other models were able to learn automatically that yes, it's negative, and now you negate it, it should actually become more positive or more neutral. Which was kind of cool at the time. Now we can look at the most positive n-grams that fall out of the model. There's some really fun examples here, but we're running low on time, so I'm gonna not go through some of these, but check out in the slides like some of the really negative phrases. It's like if you really want to crush a movie in your Yelp review or something, like there's some good stuff in here. We projected and modified the word vectors too, and changed to where the word vectors were. And now in the last just 2 minutes, sorry for going 2 minutes over, basically the LSTMs that were so powerful on the recurrent neural networks, well, just last year, Kai Sheng, who's a master's student and currently working with me and will be soon a PhD, has this great paper on recursive LSTMs. So you can actually take all these ideas we had for recurrent neural networks with LSTMs and apply them in the recursive setting too. And the main difference that we have here for standard LSTMs, remember we had all these input gates, for get gates, output gates, and so on. Well, it just gets a little crazier when it comes to the tree-structured LSTMs from Kai-Sheng Tai, but really there's a very similar idea. The main difference is that now you have to have this average of your child vectors, and you have a special forget gate for each child. So if certain words just don't matter, they don't add much to sentiment, and you can kind of just forget about them. And negation matters a lot, so you wouldn't want to forget that word and change it, and you can keep doing that as you go through the tree structure. And then those, at least last year, actually created some of the most accurate sentiment on the fine-grained data set. And this is the last sort of experiment. They also did incredibly well on the semantic similarity, which I think is a right replacement for paraphrase detection. So I don't think anybody should work on paraphrase detection as this binary problem anymore, but really look at relatedness scores, where you basically don't make these tough binary choices, but you kind of say, well, these two are on a scale from 1 to 5, quite related. And so in this model, a tree LSTM has now the most accurate sort of mean squared error in capturing similarities. Again, there's more pronounced effects for different sentence lengths, and those are all the kinds of plots I'd love to see when I look at your project reports. All right, see you on Thursday. Thank you.